Alright everybody, I hope you guys are doing well. I want to discuss with you probability and looking at Punnett squares, and when we specifically look at a dihybrid cross. So a Punnett square is a tool that is utilized in order to see the probability of the genotype and the phenotypic combinations. And so probability is the likelihood of a particular event actually occurring. And so, for example, if you flip a coin, the probability of you getting heads is going to be 50%, and the probability of tails is going to be 50%. So you have a 1 out of 2 chance that you're going to flip a coin and get heads or tails. Let's take a look at the F2 generation, or second generation. So we see that 2 out of the 4 are carrying the small t. So they're carrying the gene with for a short plant. Those are our heterozygous, and that means there's 4 possibilities of gametes that could show up in the F2 generation, but only 2 of them, 2 out of 4, are going to be carrying the little t allele, which you can reduce this to 1/2. So 1/2 of the 4 of your chances are going to carry the little t allele. So overall, when you look at the probability, you're going to see that 1/4 are actually going to be short, and 3/4 of them would be tall. Now this doesn't always occur, but these are the possibilities. This is the predicted outcome of what we could potentially see when heterozygous tall plants are crossed together. And when you're taking a look at 2 heterozygous genes coming together, you will always have a 3-to-1 ratio, no matter what. So if you cross, big A and little a together, big B, little b, no matter what, you're always going to have a 3-to-1 ratio, 3 being the dominant number and the 1 being the recessive, or the homozygous recessive number. Now, just to give some terminology, the word homozygous is going to refer to 2 alleles that are going to be identical, so big T's or little t's in our example of tall and short plants, and something that's heterozygous will have 2 non-identical genes. So the only option for that is to have a big T and a little t, and that's the terminology that we use. We do say, you can say, call it heterozygous dominant just to remind yourself that it is dominant. Terminology may also say homozygous dominant, so that's your big T. These are your big and little t's, and then your homozygous recessive will be 2 little t's or 2 little a's, or whatever the letter you're choosing to represent your alleles. So how do these alleles segregate when more than one gene is evolved? What if we're looking at a pea pod that has color and wrinkled seeds included in what we see? So what Mendel came up with after studying the pea pods and looking at their characteristics, he was able to come up with the principle of independent assortment, and that is stating that genes for different traits will segregate independently during the formation of gametes. And so we've already kind of discussed this, but we want to consider looking at a dihybrid cross, and this is when we're looking at 2 different traits. So the Punnett squares can get a little bit more tricky when you do these. So for example, we want to look at seed shape as well as seed color, and the alleles for seed shape will actually segregate completely independently of those for seed color. And so here we have the green and wrinkled, that's our homozygous recessive, and we have round and yellow, those are going to be our homozygous, and they're going to be dominant. So these 2 genes are actually not going to influence the inheritance of each other. And you can see that after we do the cross. And I'm going to show you an example of how to do this cross. So if here's what we had in the previous. That was the homozygous recessive. The possibilities as far as gametes go is that we can kind of foil this, right? If I go through meiosis and we're looking at our male or the female portion of the organism, right? I can foil out and get the different possibilities for what the alleles may carry. It may be like that, or it may be like that, or taking this one and this one, right? Those two could be stuck in an egg or a sperm, and then that one could be stuck in an egg or a sperm. Essentially, it's the same for everything. It's homozygous recessive for both traits. So it's going to be a wrinkled and green plant. Now looking at the dominant, right, I can do the same thing. This will get paired up with this during meiosis, so that's big, and it's the same exact thing as before. Everything is going to be homozygous dominant. Oops, ignore that one. We're going to cross it with this and cross it with this one. Okay, so those are all homozygous dominant. Now, when I cross it, let me go back to this page. Here's where our alleles are put. Here are the potential gametes, right? If this is the female, right there, and this is the male, he's going to contribute these types of alleles, and that's all he can contribute. So when you do the cross, you will cross all your letters. Let me get rid of some of this. And look, my R's match with the R here, so we get big R, little r, and the big Y and the little y match in this box. And you continue to do that for everything. So the ratio here, there really isn't a ratio. It is going to be 100% heterozygous. Just going to write over this, heterozygous for round and yellow. Okay? So a good trick is that any time that you have homozygous, right, you can simplify your dihybrid cross. Notice how these are all the same alleles and these are all the same alleles. Well, I could just simply do one cross. I don't have to do all of them. I can do a very simplified version. I know I'm going to get the same thing if I do the cross, every single box in the dihybrid cross, but that's 16 crosses and I don't want to spend all the time doing that. So I can do one cross and easily figure out, okay, it's going to be 100% heterozygous. Now what if I take that F1, right? The F1 in the previous dihybrid cross was heterozygous for both, and I crossed them together. What Mendel ended up seeing was he saw 315 plants were round yellow, 32 seeds were wrinkled green, and these were the parental types. These were the original ones from a couple slides ago. These were the very first. And then he ended up seeing 209 plants that had combinations of phenotypes and genotypes that he had never seen before. And so what he saw were that the alleles for seed shape had actually separated from the seed color. And so that's where he was beginning to see traits that he had not seen before. So these, just as a reminder, these traits are not going to influence each other in their inheritance, and they're going to be expressed separately. So for example, right here we see something that is little r, big Y, little y, and so that little r is going to represent wrinkled, and then we have something that's yellow. So this is wrinkled and yellow, and we haven't seen this type of phenotype or genotype yet at all. And the ratio at this point is going to be 9 to 3 to 3 to 1 of the phenotype. So there's going to be 9 of this type right here. It's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are going to be round and yellow. I will have 3 that are going to be, let's see, round and green. That's round and green, round and green. So round and green. You're going to have 3 that are going to be wrinkled and yellow, wrinkled and yellow, wrinkled and yellow, and 1 down here that is going to be green and wrinkled. Sorry, I wrote that backwards. Okay. Now, I know these phenotypes, and it's just going back to, you know, realizing what was dominant and what was recessive. Okay? Now, A special trick that can cut out the time of doing all of this, right, 16 boxes, is anytime I have two dihybrids that are heterozygous, no matter what, it's always going to be 9 to 3 to 3 to 1. And so all I have to do is determine what is going to be 9, what's going to be 3, 3, and then 1. So that's a real easy way to have a shortcut so you don't have to do all of this. And just remember that we will practice these things in class, so please make sure you bring your questions, but we're going to have plenty of practice and I can come and help you individually when you need it.